Now I will write a few standard constant values. Right, first of all we'll go through the mass of electron. That value is 9.1 into 10 to the power of minus 31 kg. Okay, in terms of kgs it should be 10 to the power of minus 31. And similarly we have to write the charge of an electron. Charge of electron you have to write in terms of negative value. If it is a positive charge, you have to write plus symbol. So here I wrote electron, that's why I am writing minus symbol. Minus 1.602 into 10 to the power of minus 19 coulombs. Units of charge, coulombs. And similarly I am writing now electron volt. Generally we have to use this word in this subject, that is electron volt. Electron volt, so now onwards we can write like this EV. So this value should be 1.602 into 10 to the power of minus 19 joule. Right, here I wrote joules because this electron volt is a energy. It's just very small energy which is used to move an electron from valency band to conduction band. So energy units are always joules, so that's why I wrote in terms of joules. So 1.602 into 10 to the power of minus 19 joules is acts as one electron volt. Or we can write 1 joule is equal to 6.25 into 10 to the power of 18 electrovolts. Joules in terms of electrovolts and electrovolts in terms of, generally in this subject we have to use electrovolt word for energy purpose because here we have to apply very small energy. So units of very small energy measures in terms of electrovolt. That's why I wrote here the relation between electrovolts and joules. And one of the very important parameter, that is a Boltzmann constant. Boltzmann constant which is denoted by K, and this value is 8.62 into 10 to the power of minus 5 electrovolt. So this Boltzmann constant we have to use a temperature. So wherever temperature is considered, there we have to take this constant. It is also called as temperature constant, right? So this value is approximately 8.62 into 10 to the power of minus 5 electrovolt per Kelvin. And from this another important word is defined, that is a thermal voltage. It is also called as a volt equivalent temperature. Volt equivalent temperature, so which is denoted by Vt. This Vt is equal to Kt by, here K is a Boltzmann constant, Q is a charge. So if you substitute those constant value in this, then it gives the T by 11,000 temperature in Kelvin. We have to write this is temperature in Kelvins, not in centigrade. So you have to write in terms of Kelvins only. And if you substitute the temperature value at room temperature, the temperature in terms of Kelvins is 300 degree Kelvins. If you substitute that value here, then the Vt value is approximately 26 millivolts. Now in this subject generally we have to use some other words like milli, micro, nano, pico, right? So first of all we have to understand what are the values, exact values of those words, right? Here I am writing one standard representation 10 to the power of 1. 10 to the power of 1 we can write in terms of deca, that is deca. And if it is 10 to the power of 2, then it is also called as hecto, and 10 to the power of 3 is a kilo. We have to use all this now, right? So kilo is denoted by capital K, and hecta is a capital H, and deca we can write in terms of capital D, right? And from this I am writing 10 to the power of 6. 10 to the power of 6 is a mega, which is denoted by capital M. So if you write this unit values in terms of capital letters, then we have to understand this value should be 10 to the power of positive power, right? If you write the positive integer here, 10 to the power of 9 positive integer, then it is a giga, which is denoted by G. And similarly we can write 10 to the power of 12. 10 to the power of 12 is a tera, which is denoted by T. and one more is 10 to the power of 15. 10 to the power of 15 is a peta divided by capital P. And similarly, we can write some other values. So up to peta values are enough based on our subject. And if you take the negative powers means like 10 to the power of minus 1, 10 to the power of minus 2, these type of values. With the negative powers, the values are defined like this. This is a deci, right? 10 to the power of minus 2 is a centimeter. It's a centi. And similarly, 10 to the power of minus 3 is a milli. Milli, which is denoted by small m like this. And 10 to the power of minus 6 is micro. So we can write this micro in terms of mu representation like this. And one more, 10 to the power of minus 9 nano, right? And similar 10 to the power of minus 12 is a pico. Up to pico enough. We have to write here small p. See, 10 to the power of positive integers. 10 to the power positive integers representation is done by the denoted by the capital letters, and 10 to the power of negative integers denoted by the small letters. Okay, you have to remember these points also. So these are also comes under standard values. And now I want to explain how to convert centigrades to kelvins. So the conversion from centigrades to Kelvin. So percentile Celsius to kelvins, degree Celsius to degree kelvins, we can add anything. So if you write in one value in terms of centigrades, that is x degree Celsius. If it is x degree Celsius, this is equal to 273 plus x degree kelvins. So to convert centigrades to kelvins, add 273 degrees to the centigrade, then it gives you in terms of kelvins, right? And similarly, from centigrades to Fahrenheit is not required. Generally, we have to use this centigrades conversion, centigrades to the kelvins conversion only. If you write in terms of 0 degree kelvins or 0 degree centigrades, that is in terms of kelvins is 273 degree kelvins, right? Room temperature value is how much here? 27 degrees Celsius. If you write in terms of Celsius, the value is 27 degrees. In terms of kelvins, this should be 300 degree kelvins. 273 plus 27, that becomes 300 degree kelvins. So these are the some conversion concepts and some constant values, how to represent all this I have explained here. Now we will go through the semiconductor physics. Here, first of all, I will start from the matters. Now see, I wrote a simple definition. Matter is some quantity which is having specific weight and occupies specific value. The basic definition of the matter. These matters are classified into three types. These are classified into three types. One is a gases, more atomic space. The second one is a liquids, moderate atomic space, and third one is a solids, less atomic space. It occupies a less atomic space. These three are comes under gases. These three are comes under matters, types of matters. Now from this I am writing the definition of atom, because the semiconductor physics starts from the atom. So atom is the smallest particle of matter which consisting of a nucleus. So atom is the smallest particle of matter. So it is the smallest particle of matter. Example, silicon. Silicon is one atom. This atom number is 14. This atom number explains the number of protons or number of electrons. This explains the number of electrons. So in any atom, number of electrons is equal to number of protons. Both should be equal. Positive charge is equal to negative charge. So internally which has a 14 electrons, so that's why the atom number is here 14. And the arrangement of this atom structure is completely defined like this. It has one nucleus. This is called nucleus, and which has electrons revolving in orbits like this. So let us consider In first orbit only 2 electrons are there, and in second orbit totally 8 electrons are filled here like this, 8 electrons. And similarly in third orbit. So this one is comes under first orbit and this one is comes under second orbit and so on. The number of orbits depends on the atom number. Now here I wrote totally 10 electrons. So this atom number is a 10. And if you want to draw the atom structure of silicon, silicon requires 14 electrons, right? So that's why it requires one more orbit, that is the third orbit. So within this third orbit, I am writing here only 4 electrons are there because this is the standard atom structure of silicon. How many electrons are there? 14 electrons. 2 electrons are defined in first orbit and 8 electrons are defined in second orbit, and in third orbit totally 4 electrons are there. So this outermost orbit is also called as valency orbit. So the electrons in valency orbit are called valency electrons. Okay, based on the number of valency electrons, these materials are classified into 3 types. Those are conductor, semiconductor and insulator. And to understand that, first of all, we have to understand one more important concept, that is a band theory. So now I'm writing the bond structure. Here every orbit has a certain band. Now I'm taking outermost orbit. Outermost orbit band is a valency band. This is valency band. In one words, I will write this valency band as a VB. And later it has another band. That band is a conduction band. Conduction band is nothing but free electrons band. This is I will write as a CB. So every atom has a valency band. Outermost orbit band is a valency band. In valency band, all electrons are bonding electrons. Those are the fixed electrons. Those are not free electrons. So valency electrons are bonding electrons. Bonding means they can't move. Yeah, those electrons are acts as fixed electrons. If any due to some external energy, this bond can breaks. Later these electrons becomes a free electrons. That means these electrons jumps into the next level. Though that level is called a conduction band. So conduction band electrons are free electrons. Now from these two I want to define a new definition here, that is a forbidden energy gap. The gap between the conduction band and valency band, here I am writing, see, the gap between these two is called forbidden energy gap. So another definition also we can write, that is the minimum energy required to move an electron from valency band to conduction band is also. Now I want to write types of energy gaps. Based on the types of energy gap, the semiconductors are classified into 2 types. Those are direct band gap semiconductors and indirect band gap semiconductors. So here just I want to explain the types of energy gap. Direct band gap, indirect band gap. Here the same momentum will occur. Here same momentum is nothing but the this is a we can write like this. It is the band gap in which the electrons at the lower surface of the conduction band and the holes at the upper surface energy of the valency band are recombined with the same moment. So the recombination process will exist with the same moment. Here I am writing the band gap, energy band diagram. So let us assume this is a valency band and here it has a conduction band. So conduction band consists of free electrons and valency band consists of holes. Now I am writing this level. Yeah, here I am indicating by the blue color. Now this one, this level is the lower case surface or lower surface energy level at conduction band. This one is I am writing EC. And similarly valency band upper level, upper case or upper surface level energy of valency band is EV now. So the band gap in which the electrons at the lower surface of the conduction band and the holes at the upper surface energy of the valency band are recombined with the same moment. So this will recombines with the same moment. Same momentum is called a direct band gap semiconductor. So we can write here the recombination process. After recombination process, it delivers the energy in the form of light. These type of band gaps are direct band gap. Here releases the energy in the form of light or in the form of photon. So we can write one important point here: due to recombination of electron hole pair, is released in the form of photon. Your photon is nothing but in the form of light, which has more light and less heat. This band gap is a direct band gap. Similarly, I won't write indirect band gap now. Now here we can write the same definition due to different momentum. In direct band gap, this momentum will be same. Now here different momentum. That is the band gap in which the electrons from the lower surface energy at the conduction band and the holes at the upper surface energy of the valency bands are recombined with different or unequal moment. And similarly here the releases the energy in the form of phonon. Due to the recombination process, the electron hole pair releases the energy in the form of phonon. Phonon means here in the form of heat. So which consists very less light and more heat. So this indirect band gap, if the semiconductor follows the indirect band gap, then it is called indirect band gap semiconductors. Those are silicon and germanium. These are comes under indirect band gap semiconductors. The direct band gap semiconductors examples are gallium arsenide, gallium phosphide. These are comes under direct band gap semiconductors. Just here I am explaining. If the semiconductors follows this band gaps, these type of band gaps, then the semiconductors are classified into two types: direct band gap semiconductors and indirect band gap semiconductors. Now the concept is based on the energy gap. Materials are classified into conductors, semiconductors, insulators. This classification we can write based on the energy gap or based on the number of valence electrons also. First of all, I will write a few definitions here. The energy gap, the forbidden energy gap, here I will write like this: the forbidden energy gap, FEG, is nothing but forbidden energy gap. Forbidden energy gap of conductors should be 0 electrovolts, and insulators, semiconductors, it should be 1.1 electrovolts. Approximately we can write 1 electrovolts, and for insulators it should be greater than the 6 electrovolts. That means in conductor, both valency band and conduction band are overlaps each other. Let us assume this is a valency band and this one is a conduction band. Now both are overlaps each other in conductor because there is no gap between the valency band and conduction band. If these two are overlaps, then all valency electrons are acts as free electrons. Valency electrons are the free electrons in conductors. In semiconductors, it has the gap. So the gap between the valency band and conduction band is a forbidden energy gap. So that gap is approximately 1 electrovolt. This should be 1 electrovolt. So approximately I wrote here 1.1 electrovolt. That gap is medium. But in insulators, the forbidden energy gap is very, very high. The gap between the valency band and conduction band is greater than the 6 electrovolts. This gap should be greater than the 6 electrovolt. That is very, very high gap. So there is no conduction in insulators. That's why we can write here carriers are electrons here. In conductors, these are the electrons. And in semiconductors, carriers are electrons and holes both. In conductors, you have to consider only electrons because the valency band acts as a conduction band only, right? And in insulators, there is no carriers, so we can write nil carriers, no carriers, or we can write like this, no carriers, because there is no conduction in insulators. That name explains there is no conduction. And now I want to write another important point. This point is important for the competitive exams. So type of bonding. In conductors, metallic bond will be formed. Metallic bond. In semiconductors, covalent bond. Covalent bond is nothing but sharing of electrons, right? So covalent bond can occur. And in this insulators, ionic bond. Type of bond I am writing now in different materials, type of bond. And another important point is a temperature coefficient. Conductors follows the positive temperature coefficient, and this insulator follows the neutral. There is no temperature coefficient here, it follows the neutral. So temperature coefficient, positive temperature coefficient is nothing but temperature and resistance of the material are directly proportional. Negative temperature coefficient is nothing but temperature and resistance of the material are inversely proportional. That means if the temperature is increases, resistance of the material is decreases. So in semiconductors, if the temperature increases, resistance is decreases. But in conductors, temperature increases, resistance of the conductor is also increases, because conductors follows the positive temperature coefficient. So this classification is based on the number of valency electrons and forward energy gap. And again we have to write the number of valency electrons here. So in conductors, number of valency electrons are less than the 4, and in semiconductors the number of valency electrons are exactly equal to 4. And in insulators, number of valency electrons are greater than the 4. So the number of valency electrons are exactly 4, then those materials are called semiconductors. Example, silicon, germanium, these are acts as a semiconductors. And conductors examples are copper, aluminium. So here the number of valency electrons should be less than the 4. And insulators, mica material acts as the best insulator. So that material, in that material the number of valence electrons should be greater than the 4. So that material acts as an insulator. Now our concept name is a semiconductor physics. So here completely we have to study about the semiconductors. Okay, just I have explained the classifications of the materials. So now I will explain about the semiconductors. Generally, the semiconductors are classified into two types. One type of semiconductor is a intrinsic semiconductor. Now onwards I will write as a SC. SC abbreviation is a semiconductor, right? And another type is a extrinsic semiconductor. So I will explain with the differences here. Intrinsic semiconductor. This intrinsic semiconductor is also called as pure semiconductor, and extrinsic semiconductor is also called as impure semiconductor. Generally, semiconductor consists of 4 valency electrons. So now in this pure semiconductor, number of electrons is equal to number of holes. Both should be equal. That means negative charge is equal to positive charge. Number of electrons and holes both are equal. That's why in intrinsic semiconductors, conductivity is very less. Best examples of semiconductors are silicon and germanium. These are the best semiconductors. And other also there, those are carbon. Carbon consists 4 valency electrons, but it does not act as a best semiconductor because sometimes it is acts as a insulator and sometimes it is acts as a best conductor. That's why we are not taking this carbon as a semiconductor. And an extrinsic semiconductor, number of valency electrons, not valency electrons, number of electrons is not equal to the number of holes here. Both are not equal. Finally, the total positive charge is equal to total negative charge. Electrically neutral we can write, but number of electrons are not equal to number of holes. Those type of semiconductors are called extrinsic semiconductor. If these two are not equal, that's why the conductivity of these semiconductors are very high. Conductivity is very high here. So these type of semiconductor forms with adding of impurity. So adding impurity to pure semiconductor is called doping. So this point is important here. The doping process is used to improve the conductivity. So after doping process, intrinsic semiconductor becomes extrinsic semiconductor. Right, so before going to this point, I want to explain one more point in intrinsic semiconductor. Intrinsic semiconductor, the Fermi level lies exactly middle of the forbidden energy gap. So the Fermi level lies exactly middle of the forbidden energy gap is energy gap. Semiconductors are called intrinsic semiconductors. And in this number of electrons is equal to number of holes. Due to that, conductivity is very less. So to improve the conductivity, doping process is used. What is doping? Doping is nothing but adding impurity to pure semiconductor. So what is the necessity of the doping? Doping is used to improve the conductivity. So after doping process, the pure semiconductor becomes a impure semiconductor. That means intrinsic semiconductor is converted into extrinsic semiconductor. Now just now I explained the best semiconductors are silicon and germanium. So the most widely used semiconductor is silicon. Compared to germanium, silicon as leakage current is very less and thermally more stable. So germanium is not used as a semiconductor. It's not a most widely used semiconductor. It is used for specific application purpose only. But silicon is the most widely used semiconductor because this semiconductor has less leakage current and thermal stability is also very high in this. And we have tried the mobility of silicon and germanium. So mobility of electrons, first of all I will write the mobility of electrons. These points also important, that's why I am writing directly all this. Mobility of electrons is 1300 centimeter square for volt second for silicon, and the germanium, for germanium it should be 3800 centimeter square for volt second. Centimeter square for volt second are the units of mobility. And similarly, now I am writing mobility of holes, 500 centimeter square for volt second for silicon, and this value is 1800 centimeter square for volt second for germanium. And observe these two here, mobility of electrons I will write as a mu n, and mobility of holes I will write as a mu p. So mobility of electrons should be always greater than the mobility of holes. Compared to the holes mobility, electron mobility is very high. And now coming to the forbidden energy gap. The forbidden energy gap of silicon is 1.21 electrovolt. Here I will write for silicon here. Forward energy gap of silicon is 1.21 electrovolts at absolute temperature, that is at 0 degree kelvins, and this value becomes 1.1 electrovolts at room temperature. Room temperature value should be 300 degree kelvins. And similarly, if you write for germanium, this forward energy gap is 0.782 electrovolt at 0 degree kelvins absolute temperature, and this value becomes 0.72 electrovolts at a room temperature, that should be at 300 degree kelvins. These are the some standard constant values of silicon and germanium. Please try to remember all this, because while we have to solve few practice problems from this concept, so there we have to apply these standard values at 0 degree kelvins. Absolute temperature values are important.